Okay, what we covered as of Friday last week was input with the input and output noise in there. And that input-output noise happened to be uncorrelated noise. So that's the situations we are working on it. So as you look at the system gain factor, we covered this last Friday about using the auto spectra and the cross spectra. There are two different ways of estimating the frequency response function, absolute frequency response function. So H using the auto spectra, and this is using the cross spectra, two different approach. Then I want you to really conduct the experiment using both approach this quarter. And Zhongwan, you spend some time to do some experiment. Are you able to get the cross spectra and auto spectra? Not yet. Okay, this week we should be able to. And as they deliver the another machine, 3563A, that I'm very familiar with, then we should be able to do. And but I feel it's better than nothing. We don't know. That's a little bit old machine. Old machine means a absolutely no good machine. No, that has been used for some 20 years in the past, and this machine seems to be but old, but it's a digital machine. So, but you may not able to print it, but using the windows in the machine, you can really experiment, conduct all the experiment that we learned here. Then I feel that's a very beneficial. The two machines, we're going to have it. As I mentioned, the brand new machine, for one machine would cost about $80,000. But we're going to buy it for $7,000, which is very, very nice, isn't it? But used. The other one is new. So I'm pretty sure we can start to conduct the experiment in about 2 weeks. So I'm going to set one group for 2 people. You can do work together, and I'll make out the experiment, the sheets, then what you're supposed to do, things like that, okay? So here is like using the cross spectra, and the other one is auto spectra. Then you should be able to measure the frequency response function. Frequency response function is also same as the transfer function, which really give you the characteristics of the system, okay? Of course, H functions are known or unknown. Unknown, right? Then you have to take a measurement. So using the input, output, the measurement, which is input excitation, then output response, then H is simply the capital Y over capital X. Things like that. That's what you want to measure it. So HA square, HC square, then divided by this guy, you can conduct the measurement of gamma xy square. Gamma xy square, which is ordinary coherence function, is a function of gxy and gxx and gyy. All quantities are measurable. All quantities are measurable. That's why gamma xy is measurable. In the measurement FFT analyzer, it has a button for gamma xy square, which means internally, as it measure the spectra, Arto and Cross spectra, then of course it can compute the gamma xy, internally compute, then put it out, the gamma xy square. Gamma xy square is a function of a frequency. So it shows the plot of coherence function value at the given the frequency, all the delta f frequency. Every delta f, it has a plot. Okay, then it shows the plot. At some frequency, it has a sudden dip, and it just comes along nicely along the value of 1. Then suddenly it goes down and come back up and keep moving nicely. The reason it goes down, I gave you a couple of reasons, like at the resonance. Resonance, what does it mean, resonance? Natural frequency of the system is very close to excitation frequency, then it shows a dip. So usually what you're going to do in the measurement is you're going to use a sinusoidal sweep, like every delta f, or every, like a fourth delta f, you can just keep sinusoidal sweep. It's a sine function, but the frequencies keep changing, keep moving. Then when it hit the resonance, then it dip. It shows a dip. That means even if input energy is very small, but it resonates. So then suddenly the response of the system getting wild. Okay, then because of the so-called impedance mismatch, that's some reason behind it to have a dip. As it has a dip, then system response is very weak. So then gamma xy square is getting small. When I say small, approach to 0, but not becoming 0. Okay, so it's less than 1. So this is what the gamma xy, this has to be less than or equal to 1. And from here, I concluded here, this HC, okay? HC has to be less than HA. HC, H absolute C square has to be less than H absolute A square. Why? Has to be HC is less than HA. Why? 7. Why? Any reason? Any STX students? I said this value, whether square it or not, this value, absolute value, has to be less than the HA value. Because I did it Friday. Friday, Sungwon was in TV here, monitor. And Sungwon, you tell me.
Because gamma xy can't be bigger than 1. So
yeah, see, so simple. But Yongwon and Chebam were very busy over the weekend and have no time to review. I'm just kidding you, Chebam. So it's better to review. Okay, you can review by, you can connect it to my lecture through internet, right? Yeah, so you can do that, right? Because you have nothing else to do after 5 o'clock. No. So as you have a time, please review it. Because gamma xy square has to be less than or equal to 1. So this value has to be less than equal to the denominator value HA. Otherwise, the division quotient will be higher than 1, which is not going to happen. So, which means this HC, the frequency response function, estimated frequency response function has a lower value if you use a cross spectra. Cross spectra, what does it mean? Cross spectra. If you're using like SXY or GXY is equal to something times SXX. What's the something? SXY is equal to H XY times like SXX. Okay. So I want you, I'm, as you may notice, I repeat the same thing quite often. Because if I look at your eyes, some of you, the arrow goes deep into the brain. Some just hit it and fell down. Okay. So we'll look at always review together. So gamma xy square, same thing over and over again. Then HA square, right? This is a definition, right? HA is H absolute A square. I should have put HA absolute square. Maybe that may be better, but anyway, you understand what I mean here. GYY is equal to HA square times GXX. Okay? So this is defined by GYY over GXX. Now, look at here. Everybody look at here. So here, this expression, there is a noise in input, noise in output. This relationship, the numerator, does it ring the bell to your mind? Oh, that's it. You have any reservation? How this is expressed as this? Visualize your diagram. Very simple diagram. Uncorrelated input noise is in input side, and also GNN in output. M is input, N is output. Can you visualize? I always insist to visualize. Okay? And the GXX has input noise, which is GMM. So you should be able to tell GUU plus GMM. And this you can express by taking GVV out, okay, outside of the parenthesis. And this is outside of the parenthesis. Then what do you call this, Sheba? I'm pretty sure you didn't have a chance to review. Not just for my course, any course you are taking, before you come back to class, always review. that helps you tremendously. Because you're a bright person. You're all 똑똑해. That's the right expression. You're all smart. So this is called, what do you call, Jusam? This is noise to output ratio. Okay? So this is noise output noise to signal ratio. This is the VV is the signal. You really have interest, right? As open loop, this is a system. This happened to be the V T. This is UT. This is H F. This is open loop. It's not closed, it's open. So if you take the same thing over again, so gamma UV, of course this is a function of F, is equal to gusto. What is it? What's the value? Youngbin, what's the value? It's a 1, see? Gusto, spend a little more time. Okay, I'll start to keep asking questions. Don't say, geez, that guy is bad. Well, in the learning, in the class, who cares, as long as we learn. That's a 1. Why? No noise in there, okay? No noise. Simple, right? You can put the equation forms. UU, GUU. This is input noise to signal ratio. We want to reduce that noise to signal ratio. Okay. So by looking at, usually this is input noise to signal ratio. We can usually call here is alpha, or this output noise to signal ratio we usually designate as a beta. VV UU, VV UU, VV UU, G VV, of course is a function of F, is H F square GUU. And GUV is equal to HF times GUU. Oh, this is not the S. Function of F. Same thing over and over again. And gusto. Gamma UV F square is what? Expression. Total expression. Gamma UV square. I didn't ask you to memorize it. You love her, you love your yachin so much, you will never forget. What's this? G, UV, Square? And? Why you do not need the absolute sign there? Why? This itself are the real. So you can change it to the u to x, v to y, okay? This is a fundamental. If you don't know this, then you're out. So GUU over GVV over GUU is H absolute square right from here. If you express the function, if you express the function, frequency response function, then you see here GNN, GMM, which is really noise term. Then you can generally say this estimate of frequency response function here is a biased estimate. Whenever you hear about the biased estimate, you have that term which is contaminated by the noise. Okay, biased estimate. If you don't have such a term, noise term, then that's unbiased estimate. So regardless, I said give a bias error. Even if this is way less than the real signal, this is in generally, you should say, oh, this is has a bias error. Noise by the noise. If noise is somehow blocked off, noise is somehow absolutely minimized, then bias error is very small, which means estimating the real signal is good. This is used GYY over GXX, auto spectra. So H is A, using the auto spectra. And now using the cross spectra, it's good. You can avoid not to use because you need the phase information to construct the frequency response estimate. Magnitude and phase is what you need to go back and forth from time domain to frequency domain. So HC is what you really need to get the phase. Using the HA, you only get the magnitude. You don't get the phase. Right? Charu, say yes. Not clear? Clear? H absolute C is GXY absolute over GXX. You don't have to put the absolute here. In this expression, GXY is equal to H. You can put H. You don't need really HC, but HC times GXX. Same as shown over here, this. Then you got the phase and magnitude together. GXX is this guy plus that guy. what condition do you have to put it out here? M noise, input noise, is uncorrelated. It's coming from motors from some other source. Has nothing to do on this system. So G xy is equal to, so I said over here this is equal to G uv. Why can you, how can you say that? Gxy is equal to GUV. Can you click your heart right away? Here. This is the Gxy is equal to GUV. We have done this. Can you bring back in your brain? Because M and N are uncorrelated. Whenever it couples, M couples with X or M couples with N or whatever, uncorrelated. That's a zero. So it purely should have this guy happen to be this guy for uncorrelated noise. This is equal to this. Is that? You divide by top and bottom by GUV absolute, then you have this times that. If you look at this guy is slightly different from the expression. If you look at this function HC, this function, this is for estimate, both are, this guy is this, okay? This guy or this guy, both are estimate the frequency response function with the noise term in it. If you look at here, this is not the function of output noise, isn't it? You buy that? Jamin. This is this term, this is estimate of HC squared. The HC absolute has no output noise in here. Even if output is very high, and that's not the function of output noise. But the other one is output and the input noise. So in the experiment you can try out. We have a couple function generators, so you can try out. This is last week of April, and on May we have 3 weeks, right? 3 weeks, so which means second week of May, maybe starting the first week of everything, if everything goes well, starting with first week of May, you can do the experiment. Just this year, you don't have to write reports or anything, but I want you to have enough time to really conduct the experiment and read all the data in the windows in the FFT analyzer. It's better than nothing. Okay. So here is independent of the input output noise here. What case all this belong to? Uncorrelated situation where the uncorrelated input and output noise there. If you memorize, you can't even memorize equation, nonsense. You're not going to memorize. But understand what does it do. That's 100 times meaningful. And over here, output noise is only situation. Of course, we have done it, but we concentrate one parameter to another parameters. So in this case, it's output noise only situation. I'm going to designate H1 as a measured frequency response function, measured. If I replace this guy, which means measured, this is anyway system transfer function. What's the difference between transfer function and frequency response function? Gusto, what's the difference? What's the difference? Frequency response function and the transfer function. I keep saying both, right? Say same. It's the same. Okay? Nothing to confuse. Well, Yongwan sometimes called Temin. Temin. He changed his name. So Temin. So transfer function. Some control people. I'm not kidding him around. You know, that's what happened. Transfer function. Control people called the frequency response function as transfer function. Same. But the area they are working, they always call the transfer function. So don't feel there's a difference, okay? So H, this H is the true transfer function. What's the difference between the measured and the true? True means no noise in the system. Okay, measured has a noise in the system. So, okay, noise in the system. X is measured as is from the shaker. That's the input. Assuming here is no noise. Noise is, it said, is only in the output. Okay, we really study all different cases, all different situations and all that. That's what we are doing it, then keep doing it. So when this is signal, this is collection station transducer. You will see the transducer, real transducer. We have a charge, so-called the charge type transducer, not the ICP type transducer. ICP type is like integrated circuit, is all miniature circuit, is all implemented in the transducers in there. Then electronics in there, expensive, right? Then the charge type transducer is cheap and a little bit bulkier, but it measures very good. But it generates very small the voltage. Very small means millivolt. So millivolt is very difficult to really measure. So what we have to do is we put the so-called charge amplifier. It amplifies the signal. Okay? It amplifies the signal because it's so small, millivolt. Then you have to boost up the amplitude. So you have to hook up to a signal conditional. Signal conditional, what that does is it pick up such a small signal, it amplifies it. Then that's you use a signal conditional. So charge transducer, you have to have a signal conditional to amplify it. So what you want to do, whatever I explain here, I don't have to explain in the lab, I hope sometime next week, toward next week. Joan, I want to really conduct the experiment next week. Okay. So, so here, the noise, the still uncorrelated noise. From next topic is going to be correlated noise. This is kind of the last lecture on, oh, that's not true. This is about the last lecture dealing with uncorrelated noise. Then we're going to deal with the correlated noise pretty soon. So here is uncorrelated noise measured in the transducer. V is what? V is a true signal, no correlated, no noises in there. So if you look at this open loop here, this open loop, you can tell the GXV is equal to H times GXX, or GVV is equal to H absolute square times GXX. So GXY is equal to H1 GXX. I'm not dealing with the V, right? GXY, GX measured, right? So it's H1, not the H. H1 is the measured, the frequency response function, clear, H1. H1 is said here is unbiased estimate. Why is that? Why is unbiased estimate? I'm asking myself. And this is, he said, true estimate. This is, oh, I'm sorry. Unbiased means no noise is involved. Why is that? Well, let's think a little bit, okay? And this H, let's hold this definition. By looking at this, this is measured, this XY. Y is V plus N, which means noise has to be involved here. But I said here, H1 is supposed to be, in common sense as of right now, that's supposed to be biased error. Has to be there. So it should be biased estimate. Biased estimate. Noise is gonna show in there. But let's wait for a minute. But going here, by the way. And this is a true estimate. True H is equal to GXV over GXX. Make sense or not? These statements, H is GXV over GXX, I said here. Is it true? Is it yes? Yes. Why? You're looking from here to here. No noise contamination in there. So GXV is equal to H times GXX. That's what this is, right? Yeah. Then now GXV is equal to GXY minus G. Don't put the cross line here. GXV is equal to GXY minus GXN. In other words, GXV plus GXN is equal to, Can you feel it on this? Here. gxy is equal to gxv plus gxn. You can feel it. It's good. Or if I write the xv plus xn is equal to xy. You feel it? This is in Fourier transform domain. Or I can write this guy v plus n to, you have to have a conjugate to do the in expressing time domain. X star v plus n. You should put the this is conjugate sign. Right? Up to here is enough. So if you do that, x and n, the signal x has nothing to do with the uncorrelated noise, isn't it? Say yes. Yes. Then I can say this is equal to 0. So which means this is equal to 0. Then what can you say? gxy is, in this case, is gxv, right? So over here, this is equal to this, right? Then this is a zap to gxv over gxx. This guy is gxy over the gxx over here. I pull the arrow up to here. After I wrote this, I feel some of students may confuse. So I put another line in there. But as I explained, this is clear. So here, gxy is equal to gxv. gxv is from here to here. Noise is not here. From here to here, noise is there, but it's uncorrelated noise. Then gxv is equal to gxy. I can replace, in this expression, you can tell whether this guy is, you can say, unbiased estimate, because y is noise contaminated. But what kind of the noise? Uncorrelated noise coming from the third world. So I can say this guy is equal to this, right? I can replace this as a gxv, right? gxv then is identical to this. This is a true. The transfer function estimate. This is equal to this. Then is noise-free estimate of a frequency response function. What I am claiming there, in this case, is H1 is equal to the true. That's what I'm claiming. When output noise is uncorrelated. Okay. It's all this guy. I think you understood. As I see your face, you understand really well. Shouldn't be a problem. This is really nice. If you really taste all this spectra estimate, it's really beautiful. So GBV is equal to H1 absolute square. In this case, H1 and HR Same. No difference, right? True. Makes sense? Because this guy is equal to this guy is equal to this guy is equal to that. So GVV is right here. So now it's around here. GVV is equal to transfer function H or H1 in material square times GXX. Right here. And after that, you can just replace those guys, make it simpler. What is this? This guy is coherence function. So times GYY. So GVV measurable? Yes or no? GVV measurable? Answer me. No, GVV is not measurable. All you can measure is GYY or GXY. So GVV not measurable. Okay? But is it calculatable? Because GYY you can measure. Right? And the gamma XY square you can measure. Well, you have to compute, right? But all the components, GXY, GXX, GYY are measurable. Then gamma XY, right after you finish the measurement, gamma XY square is computable. So this guy is computable. This guy is directly measurable. Then GVV is calculatable, computable. That's very nice, isn't it? Then I can say, I can ask GNN, is it computable? Is it measurable? Can you find GNN? GNN is noise contamination level. Noise contamination level. Noise contamination level. It's output noise we have. It could be whatever. Okay, GNN. Using the circuit, the diagram, can you measure GNN? Can you compute GNN? First question, can you measure GNN? Yes, raise your hand. If you say yes, I'm going to just walk out. Is it computable? Yes, it is computable. How? Well, right here, this relation here. This is this. Is it measurable? Yes. Is it computable? Right here. Yes. Then you can compute GNN. So GVV is equal to gamma XY squared GYY, and you can have that, right? This is to explain this again, but I already explained. So GNN is equal to GYY minus 1 minus gamma XY squared. It's interesting. I'm going to stop right here. If you have any question, don't hesitate to stop by to see me. Okay, I'll see you Wednesday.